Good morning, everyone. Thank you for joining us today. My name is Lynn DREISILKER, and I am the Marketing and Branch Operations Manager at DREISILKER Electric Motors. We are excited to have our vendor, MH&W, here to talk with you about how CoolBLUE can help you in your variable frequency drive applications. If you have any questions during the presentation, please go ahead and speak up. We also have the chat feature that you can type any questions you have. We will be monitoring the chat and any questions coming through. We will also have time at the end for more questions. So today I'm happy to introduce our speaker, Dave Rollins. He is the Engineering Manager at MH&W CoolBLUE. He has over 25 years of experience in the industry and has been with CoolBLUE for over a year. Dave, welcome.
Thank you very much, Lynn. It's a pleasure to be here. And I welcome everybody that's taken the time out of their busy schedule to sit in on the presentation. And I hope you guys learned something. And like Lynn said, feel free to ask any questions. I'll have a short question and answer session at the end. But feel free to stop me during the presentation if need be. And we also have Christy Giles as part of the session too. She's an MH&W field applications engineer for the CoolBLUE product. So she'll be assisting me in any questions that come up that I cannot answer. So let's get started. CoolBLUE inductive absorbers and the NALA line absorbers. So today we're going to be discussing the problems that are associated with VFD drives, the solutions, the tools, and then the CoolBLUE and NALA application guide and installations. And we'll go over some real industry solutions. In a VFD system, each pulse is not a clean square wave, as you see in the picture. Each rise and fall time of the pulse has an overshoot or a transient overvoltage. This overvoltage phenomenon is also known as reflective wave, transmission line effects, or standing wave. The per unit overvoltage magnitude is dependent upon drive cable, motor circuit dynamics defined by drive output voltage magnitude and rise time, cable surge impedance characteristics, motor surge impedance to the pulse voltage, cable length, and spacing of the train of pulses by the PWM modulator. So basically, it's a phenomena that happens. It can't really be predicted as far as how bad it is, but it does. The VFD does basically create these overshoots, and the solution is try to reduce them and eliminate them as best we can. VFD systems are not sinusoidal, but are continuous generation of pulses, as you saw on the previous slide. The pulses have a constant voltage and a dV/dt rise and a fall time of the pulse. The original VFD systems were based upon what they call a bipolar junction transistor, which were slower, and you didn't have this. You had the effect, but it wasn't that bad, and it didn't really affect a lot of the motors because of the slow transition times. But now that the VFDs are used at what they call an IGBT, which is an insulated gate bipolar transistor, the systems have now a faster switching time, a faster dV/dt, which does give you lower switching losses and a more efficient drive, but it creates problems associated with the system's performance. These new IGBT drives introduces parasitic currents in the form of two potential destructive characteristics. A, being transient voltage, harmonic distortion, and reflective waves, and B, a higher magnitude of electrical ground noise current, which is what we're going to focus on. There are commonly three solutions to this problem to remove the effects of the damaging currents on VFD motor systems. Number one is a shaft grounding device, commonly known as a current diverter. Number two would be an insulated bearing. And number three would be an inductive absorption device. For the first solution, which is a shaft grounding device or current diverter, it's a mechanical brush that rides on the motor shaft. This device attempts to divert the current directly to ground via the motor casing through the brush. Unfortunately, there's a whole series of problems associated with this type of a device. First, brushes must be properly maintained, replaced, and the system can become expensive over time. The brushes lose contact with the shaft over time due to high current flow and heat contaminants and physical wear. This method does not absorb the voltage or current. The shaft grounding just diverts the voltage to ground and does not actually absorb the current. If the system ground is insufficient, then the path could be through other parts of the systems. I believe that makes sense, that if you don't have a good ground, then the voltages and the currents will find an alternate path, and this is what creates problems in other systems. It must be maintained and replaced periodically, causing downtime for maintenance. This solution is only targeted at protecting motor bearings. A significant problem in the field is with stray capacitive currents flowing to other motor system devices such as sensors, detectors, and any other type of system communications. Shaft grounding just adds to this problem by allowing current to flow into the overall systems associated with poor grounding. A 75 horsepower and above motor must have isolated hybrid bearings on the opposite end to force the current through the brush. Added cost and maintenance time is a result for these larger motors. Number 7, literally hundreds of choices of solutions with the shaft grounding devices. That is, you have to epoxy, drill, and tap. You have shaft size varies per horsepower or kilowatts. You have washdown applications, chemical, harsh, environment resistant, hazardous conditions, and you can have poor grounding of the motor casing. And number 8, while the voltage is part of the formula of power, watts are the destructive force as what causes your damages to the motors. For example, let's say you have 30 volts times 1 amp. That equals 30 watts of power, because the formula is just V times I is equal to watts. So if you have 30 volts times 0.1 amp, so let's say it's a high voltage, low current arc, you only have 3 watts. So absorbing the current at the source near the VFD before it gets to the motor is the solution, not diverting it somewhere else after the current flows through the motor. So the next solution would be insulated bearings. Again, this is a mechanical solution where the motor bearings are made of an insulated material or insulated coating. There are definitely problems associated with this solution too. Number 1, they're expensive. The insulation bearing costs, replacements, they do not absorb or remove the actual current flowing. Number 2, motor bearings do have to be replaced, increasing the expense over time. Number 3, the solution only attempts to protect the motor bearings. And number 4, the increased heat in the system because the motor cannot provide a path for the current. So it's like, basically, to sum it up, I mean, it protects the bearings, but that's it. It doesn't even give a path for any of the damaging voltage or currents to go to. So it's just, again, a Band-Aid. The third solution is an inductive absorption device called CoolBLUE. It's the only solution for permanently removing the damaging current is to install a common mode choke around the power conductors going from the VFD to the motor. CoolBLUE devices actually absorb the damaging currents at the source of the noise, well before the damaging currents reach the motor. The CoolBLUE inductive absorbers actually absorb the energy, and they actually take the energy and convert it into heat. This is a permanent solution and not a Band-Aid. What's a common mode choke? A choke is basically an inductor. It's used to block high-frequency alternating currents in an electrical circuit while passing the lower frequencies. In VFD applications, so it basically allows your 60 hertz current to pass through, which is what we need for the motor to operate, but it's going to block all those high-frequency currents that causes the arcing and the damages to the bearing, and then also with the interference to the other electronic devices that are attached to the system. The name comes from blocking or choking high frequencies while passing low frequencies. It's a functional name. You know, the name choke is used in an inductor, is used for blocking or decoupling high frequencies. So it's pretty self-explanatory. A little bit repetitive there, but just trying to get the idea across that you were basically choking or blocking these unwanted high frequencies. A common mistake with CoolBLUE is to look for a reduction in shaft voltage. Clearly, a choke in this case, CoolBLUE, reduces current, not voltage. So it's a current device, not a voltage device. A certain manufacturer of shaft voltage diverter rings attempts to disqualify CoolBLUE with this misinformation. Again, a choke in this case, CoolBLUE, absorbs high-frequency current, not voltage. Clearly, the competition attempts to mislead the market with a Band-Aid instead of a clearly superior solution for their customers. A note of importance, CoolBLUE inductive absorbers have two functions in a VFD motor system versus just the one with the other solutions, which is just to divert the voltage. It reduces the damaging common mode currents, and it reduces the high-frequency DVDT, thereby reducing the current further by increasing the system impedance. So the high DVDT was on that very first graph of the square wave, that sharp ringing. It actually will knock those peaks on those ringing down, which basically improves your system performance. The simplest and safest way to measure these common mode currents is with a flexible clip-around Rogowski coil, as shown here. This method is used to measure high-frequency destructive common mode currents in motor drives. These frequencies are in the kilohertz up to several megahertz. This is really the only method to be able to measure these kilohertz and megahertz frequencies. The high-frequency Rogowski coil simply connects around the 3 power phases of the cable going from the drive to the motor to measure the common mode current, as shown here in the picture. If multiple cables per phase, the coil would still go around all cables. So if each phase had 2 conductors, you'd then put it around all 6 cables. The output of the Rogowski coil connects to an oscilloscope, preferably 100 megahertz and above rated oscilloscope, and then you basically measure the common mode current on the oscilloscope. You simply power down, replace the Rogowski coil around the 3 phases of power up the system, and measure the current. It's that simple.
Hi, Dave. This is Lynn
Yes.
from DREISILKER. I want to mention that we do at DREISILKER have a Rogowski coil, and if you're having issues with one of your motors on a drive, we can help you out and measure to see if it is the drive that is causing the problems.
Good to know.
Thank you. Yep, thank you, Lynn. So measuring common mode current and shaft voltage. Measuring just the voltage won't show how much current. Measuring just the current won't show how much voltage. However, when you put them both together on the screen at the same time, it shows the voltage and the current effects of the CoolBLUE. For example, the yellow signal in channel 1 indicates the shaft voltage as measured with a voltage brush riding on the motor shaft. The blue signal in channel 2 shows the current measured with a Rogowski coil around the 3 phases of power cables. Figure 1 shows before the CoolBLUE installation, and figure 2 here shows after CoolBLUE installation. So you can see, so here's your voltage, here's your current. Again, CoolBLUE affects the current, so that's really what we're concentrating on. And you'll notice how this peak and all these peaks have basically been greatly diminished down to this level. So on this one, we're looking at 1, 2, basically 3 divisions on the oscilloscope, and we've knocked it down to about 3/4 of 1 division just by installing CoolBLUE. That's the only thing that was done. As you can see, the voltage stays the same. This is just basically a zoomed in, more detailed view of the previous slide. But the current is greatly reduced. And equally important, the high frequency and ringing are reduced. So again, so here's your voltage. Obviously, there's some noise or going on with the voltage wave shape right there, right there, and right there. And you see what happens. It causes these high frequency current spikes to happen. We put CoolBLUE on, and at those same transitions, you'll notice how those high frequency current peaks are greatly reduced. Here we're up at almost two divisions. That's been reduced down to about 3/4 of 1 division. So this was done strictly with the Rogowski coil, which is available through DREISILKER. So with this simple test, it's clearly visible that current is greatly reduced, regardless of what the voltage is measured. By reducing current, CoolBLUE has effectively removed the damaging power.
What kind of currents are you looking to get below?
Typically, what is each motor, based upon the bearing size that's in a motor, there's basically maximum current limits that those bearings can handle before they start the deterioration within the bearing. And so we have charts that basically for every bearing size what those current levels should be below. So it's generally, like I said, it's just not one number. It's all going to depend upon what bearing is actually in the motor.
Could you send me those charts?
Yes, we can actually provide that through Lynn at DREISILKER.
Okay.
Okay. So going on, let's see.
Do you ever measure the shaft voltage directly with a probe on the shaft while you're checking with the Rogowski coil as well?
It's possible, but it's generally not. It's probably more likely to be done in a lab environment, but out in the field, it's not preferred because of the safety hazards in getting into that part of the motor and everything like that. It's generally not advised, and that's one of the big negatives.
I do testing all the time. I'll do like a whole paper machine on all the motors with a probe right on the shaft. We're able to get in there most times. The only time it doesn't work is if the keyway goes right up to the end bell.
Right. Okay. Yeah, I mean, it's possible if you can get in there. I mean, it's definitely something that you can measure the voltage there. So
we generally shoot for less. Oh, go ahead.
Go ahead.
We usually shoot for less than 5 volts when we're measuring it on the shaft, and if we're above that, then we'll start doing preventive measures on the motors.
Okay.
And we've seen them as high as 700 volts, amazingly.
But again, like I said, and we'll continue on with the presentation, but it's the current that we also have to look at, and that's why you really need to have, if anything, you need to be checking both, because 5 volts at 0.1 amps versus 5 volts at 10 amps, that's a big difference. So
I understand. Yep.
Okay. So the other product that basically goes along with the CoolBLUE is what we call a NALA, which is a nanoperm line absorber. It's a differential choke that increases the reliability of the system by further reducing the noise and peak values of the current. These cores must be placed around each individual wire, not around all phases like the CoolBLUE. And this NALA is to be used in conjunction with CoolBLUE common mode choke cores. So the solution is really both the NALA and CoolBLUE being used together. As you'll see in the following pictures, NALA reduces the dVdt of the high frequency charge and subsequent ringing. So here's an example. Here's your ringing. You put the NALA on there along with the CoolBLUE, and it knocks it down substantially. And ideally, you'd want a perfect square wave is what we're striving to get.
So we're purely talking about AC motors, right?
Right now, yes, we're talking about AC motors. But actually this slide mentions it here. These can also be used on DC motors, servo motors, etc. So the inductive absorbers, it's the common mode choke solution. The advantages of this solution. Installation is less than shaft grounding or insulated bearings. It's easy to install around the power cables. We can reduce the line noise by a factor of 4 to 1 or better. It can be retrofitted to any system with little effort in the field. We reduce the transient voltages, straight capacitive currents, and common mode currents before they reach the motor system. So we're nipping it at the bud right at the VFD. Small number of cores fit all motor applications, AC, DC, servo, etc. Other electronic devices in the system like sensors, monitors, metal detectors are protected as well as motors. This is a key thing which none of the other solutions do. It's a lifelong solution. The magnetic properties do not degrade over time, nor are affected by heat. So this is a solution and not a temporary fix. It's a permanent solution. Once they're on, they're good for eternity. They will never ever degrade. So you put it on, you walk away, you'll never ever have to come back to them again. That's a
Hi, Dave.
great
this
advantage.
This is Lynn from
Yes.
DREISILKER. We had a chat come in from Joe, and he said that they use insulated bearings in conjunction with grounded brushes to successfully protect larger motors. And he also noted that he feels that CoolBLUE could also be used in conjunction with grounding brush rings. Would you like to talk about that?
Yes, I mean, if you have a system currently with grounding brush rings, you can definitely put CoolBLUE on there. You wouldn't have to remove the grounding brush rings, and we actually would recommend that, because what's going to happen is over time, your grounding brush rings are going to fail. As I mentioned in earlier slides, they're going to get dirty. They're going to start losing connection, and so they're going to start to fail. But what's great is if you have CoolBLUE on your system, you don't have to worry about that, because CoolBLUE is just going to continue to do what it does, and it's going to eliminate the problem.
What you want to
so,
lunch?
Okay.
Okay, go ahead.
Yep. So we'll talk real quickly about basically how to apply CoolBLUE and NALAs per your application. First, you determine the motor size by horsepower. then you have to determine your cable length from the VFD to the motor. And note that, if you have parallel cables in the system, then each phase has to be taken into the calculation. For example, if the cables are run from a drive to a motor per phase or at 100 feet of run, then the cable length would be calculated as 3 times or 300 feet. So if you have 3 cables for each phase, you're just going to multiply your run by that, the number of cables. Otherwise, if it's just a single cable system and your motor is 100 feet away, your cable length would be 100 feet. You would then reference the VFD application guide, CoolBLUE cores per power range and cable length as shown below. And these application guides are available through DREISILKER. The cores come in 2 configurations.
Hi, sorry, Dave.
Go ahead.
This is Lynn from DREISILKER. If this is confusing for you or you would like us to help you figure out which CoolBLUEs you need, our counter representatives, sales representatives are trained to figure out which CoolBLUE you need.
Thank you. The cores come in 2 configurations, one being round and one being oval. Certain configurations, sometimes an oval core is better suited to pass your conductors through versus a round core. Electrically, they're the same. It's just really a mechanical preference as far as the number and the size of cables, what works best in your particular applications. Again, DREISILKER could help you probably steer you in the right direction in this. As you see on the screen, this is basically the application guide. Right here is your horsepower, range of your motors. Here's your cable lengths on the left side, the left column. So it's just a matter of, if you have a 75 horsepower motor, that means you're in this column. If you have 150 feet of cable, so you're going to use 4 CoolBLUE cores. And here's the part number for those particular cores you would use. And it's very important that you use the cores that's called out for. You don't want to use a smaller core, and you really don't want to use a larger core if you don't have to. It costs more money, and it doesn't make sense. The NALA, which is the differential mode line absorber, which this is a core that's going to go on each individual line. So most applications, you're going to need a minimum of 3 of these. Again, it's the same scenario. You look at the motor size by horsepower. You look at your cable length. Then you use the NALA application guide to figure out exactly which core part number you need and how many. So again, let's say in that same 75 horsepower system we talked about, here's your part number for the NALAs. And then for 150 feet of cable, you're going to need just 1 NALA. Times 3 for your 3 phases. So you'll need a total of 3 NALAs, 3 of these NALAs right here, the N29HP41-102. For these part numbers for the CoolBLUE and the NALAs, we actually built in some knowledge in the part number that, as you use these more and more, you can learn as far as what it means. It starts off with either CBO, CBR, or N for NALA. So it's either CoolBLUE oval, CoolBLUE round, or N for NALA will be your first either 1 or 3 digit letters. Then we have the inner core dimensions in millimeters. So in this particular example, it's a 68 millimeter ID core. Then you'll have your horsepower rating. So we got your horsepower, and this particular part number, this is for a 51 to 100 horsepower application. The A stands for amp, and this basically, the 6 specifies the max asymmetric current or the sum of the peak currents that this core can handle. So this particular part number, this has a 68 millimeter ID. It's good for a 51 to 100 horsepower motor, and you should be able to handle about 6 amps of peak current. So we'll talk real quick about the installation of the CoolBLUE cores. One of the most important part of the installation is that if you have a shielded cable and also a cable with the ground wire, that this must be removed or peeled away before inserting it to the cores. The shield and ground bypass the cores, providing an alternate path around the cores and effectively disabling the core functionality. So if you were to replace this, if you were to put this ground wire through the core, you're basically cutting out the cores and you're making the cores non-effective. I basically say they basically become a block of wood. They have absolutely no magnetic performance just by putting the ground wire through there. And that's not just the ground wire. It's basically any conductive wire through there. You could put a metal hanger through there. That would also disable the cores. So through the ID is should be only your L1, L2, and L3 lead. Shielded cable, again, you have to peel back the shielding so that none of the shielding around your cables is going through there. So it's just the copper, just the main copper of L1 and L2 and L3. Very, very important. I'll repeat it 50 million times because it's so important. The correct installation of NALA cores. Again, as I mentioned earlier, a NALA is going to be over each individual line, as shown here in the picture. So in our 75 horsepower, 150-foot application, it was 1 core per line. So you put one on L1, one on L2, and one on L3. Again, no grounding no grounding wire, hanging wire, or any type of conductive wire should go through there other than your L1, L2, L3 leads. Again, and no type of shielding can go through. The NALAs are always installed in the direction of the motor. So if the VFD is up here, the order of installation is CoolBLUE and then the NALA, as shown in the picture here. Here's your VFD, you got CoolBLUE and NALA. That's the preferred arrangement.
When do you use the NALAs? What's the reason, or what's the break point for putting those on?
All the time. There is no break point. The NALA adds in with the DVDT filtering and some of the noise suppression. So it's recommended that they're installed on all applications because the whole solution is really a combination of the two cores put together.
Okay.
It's like trying to eat a peanut butter and jelly sandwich without the jelly. It just doesn't work. So again, this is doing some reiteration here. So the correct installation of CoolBLUE and NALA cores. CoolBLUE, all power cables must go through the CoolBLUE as shown below. No grounding wire or shielding. In the case of multiple conductors, all power conductors go through the cores as shown here. This looks like there's, I think it's 3 cables per phase. And then the NALA, you must have at least 1 cable per phase on each cable. This picture doesn't show the NALAs, but then you would actually have a NALA here, and a NALA here if this is 3, 3, and 3. So some important notes. It is important to use the correct number and type of cores that's called out on the VFD or on the application guide. One side note, on motors up, basically 10 horsepower and below, instead of just placing the wires to the cores, you actually have to run the wires to the cores twice, and basically create two turns through the ID of the core. So you have to put the wire through, loop it around, and put it through again. And that's only on 10 horsepower and below applications. No other application would this be required. Data in the application guide is for information and guideline purposes. It's best if you contact us at MH&W or at DREISILKER to make sure that you're using the right number of cores and everything in your application. As I mentioned, round and oval shaped cores are for ease of installation and mechanical functionality. They have the same electrical absorption. The cores are installed on the load side of the drives. They can be installed on the line side of the VFD as well to reduce conductive and radiated emissions back to the grid. Again, if you're looking to do that, you definitely want to contact us. And generally, it's basically the same cores that you use on the output of your VFD. You can also use those on the input. But it's best that you would go ahead and contact us. If possible, you should try and install the cores within the drive cabinet. And you want them doing as close to the VFD as possible. You don't want to put them on right at the just on the inside, the output of the drive cabinet. You want to put them right below the VFD. Do not place conductive wires other than the motor wires to the cores for any reason in the application. We do sell brackets that can be mounted inside of a cabinet if you choose to do it with that method. And then typically most people use cable ties to if they just don't want their cables hanging loose inside the cabinet, or they feel there's too much weight hanging on the leads. You can use cable ties to hold the cores together, and then you can use cable ties to hang them and provide some relief on the weight. But they have to be the plastic cable ties, and they can't be. There's some newer cable ties that have the piece of metal that's inside of the plastic. That would be a no-no. The NALA installations, basically same straightforward as with the CoolBLUE. Again, it's important to use the correct number and type of cores per the application guide. The NALA cores go around each individual power cable. The data in the application guide is for your information and guideline purposes. You can contact MH&W or DREISILKER for detailed information if you need it. Again, they're installed on the low side of the drive only, and they would be installed after the CoolBLUE. And again, you don't place conductive wires other than the motor wires to the cores, including, like I said, the wire ties with the metal inside the plastic. So we'll just run through some pictures of some typical installations in drives. I'll just kind of like point out where the different cores are. Here's a CoolBLUE here. I believe the NALAs are sitting down in there. Here's a really good picture here. Here's your CoolBLUE cores. You see how here they use the plastic cable ties to hold them together. There's your individual NALAs. Your drives right here, right up here. Another installation. This particular installation, they're actually using a combination of the round CoolBLUE with the oval CoolBLUE. Again, electrically they're the same. They're just mechanically two different shapes. Here it shows the NALAs going over each lead. Another example here. Here's oval CoolBLUEs, and right down here you'll see your three NALAs then going over each lead. Another installation. This is your ideal. Here's your VFD. Your cores are right up here, right at the output. Here's your NALAs together. Another application, CoolBLUE cores. So the CoolBLUE and the NALA cores, they're actually installed inside of a plastic pre-made case. The material inside of them is what they call this nanocrystalline tape ribbon. It's a type of metal that's actually doing the absorption of this high frequency energy. The plastic case actually has a better performance than epoxy coatings. The other way to protect the metal cores is to basically put an epoxy coating on there. but that tends to be more expensive, and we find that the plastic case is a better solution. That can be used in outdoor applications, wet conditions. They can withstand temperatures up to 140 C. Handling is much more robust, and they typically do not break if dropped. And the cost of putting them inside this plastic case is lower than any other type of coating, especially epoxy, that type thing. One thing to note is that if they do come out, if the plastic case does open up and the core does come out, then it's best that you power the system down and you replace the core. This material is very brittle, and it's like a glass-like structure, and you don't want to be messing with it because it can break into small shards. You can get it stuck in your fingers and have an aggravating little sort of like a splinter in your finger that will drive you nuts. So if one comes apart, carefully remove it and replace it with a new core. Don't try and reuse it or anything like that, because chances are the materials, you don't want it to be breaking up on you. So go through some applications. Paper plant manufacturer, 150 horsepower VFD motor system. They had 350 gauge per phase of cabling. The customer was experiencing shutdowns, known as ghost, of their system. And they also had premature bearing failures on a 150 horsepower motor system. They were getting fluting and had to basically repair the bearings every 8 weeks. We put 4 CoolBLUE cores were put on the cabling. Current reduction of over 75% was seen, which resulted in no bearing fluting, frosting, etc. Equally important was there's no more random or ghost system shutdowns because of high frequency stray grounding currents. This is a large chiller manufacturer. Was experiencing bearing failures with within 2 to 4 years. Manufacturer opted to use ceramic coated bearings on new builds and customer repair replacements. The cost was high to build and replace. Customers reported still having failures in the field. The solution, basically all new systems at the factory and in the field rebuilds with ceramic coated bearing systems are now built with 5 each CoolBLUE cores placed around the cabling. They had a reduction of over 85% in the high frequency current. End result was 10 plus years of no bearing fluting, frosting, etc. Failures with their standard steel bearings. So they were able to eliminate the cost of the ceramics, and they've been going 10 plus years now with no failures. And that was on a chiller. Example number 3, major hospital system in New England. The air handling and pump system experiencing bearing failures in short period of time. The customer had previously installed shaft grounding rings, but still experienced failures. Unable to install on large vertical mount motors. The operating rooms were critical to keep at a constant temperature. The solution, they installed 4 CoolBLUE cores around the cabling for common mode noise. The bearing currents were lowered by over 75%. It's been now over 4 years, and the system hasn't failed. Application example 4, large manufacturer of candy experiencing random shutdowns of their system, faulty reading on metal detectors and other sensors, and random manufacturing failures, shutdowns. The common mode currents were measured at nearly 12 amps on a 30 horsepower VFD system. Bearings were failing within 6 months. Metal detectors were being slowed down because of the false readings. So we installed 4 CoolBLUE cores were placed around the cabling for common mode choke to reduce the motor bearing wear. 1 each Nala cores were placed around each individual cable line to reduce the frequency even more and to substantially reduce stray grounding currents. The bearing currents lowered well below the level of destructive force. More importantly, no more sheet metal no more metal detector-based issues. Company increased revenue due to increased speed of the metal detector without false readings. again, I hate to reiterate it, but that's one of the major benefits of the CoolBLUE NALA system is it helps prevent these other issues that people have with metal detectors and sensors and that type of stuff. None of the other systems will do that. We have several testimonials, and these would be available through DREISILKER if you wanted to share them with your customers. This was with Brady. Basically, they installed CoolBLUE chokes. And now it's part of their bill of material, and they've been extremely happy with the results that they've seen from Brady. Another Boston's Children's Hospital. I won't read through the letter, but again, same type thing. Well, this was that previous application. It's been 4 years since installing CoolBLUE, and they're still working great. But they went ahead and actually sent us a letter of testimonial as far as the success that they've had with CoolBLUE. So closing comments. The CoolBLUE and NALA continues to have tremendous success in thousands of installations worldwide. The CoolBLUE and NALA is a solution and not a temporary short-term Band-Aid to an age-old problem. CoolBLUE and NALA are now being used and promoted by major OEM drive manufacturers, OEMs, HVAC chiller equipment, wind turbines, and end users to keep their equipment functioning properly and to avoid downtime. You just call DREISILKER, your local CoolBLUE representative today, and have your VFD problem solved permanently. DREISILKER offers... Oh, wait, yeah, just one last thing. DREISILKER offers support. They have expertise with 5 Illinois locations. They have counter representatives that are ready to help you with any of the CoolBLUE questions you may have. Their offices are in Glen Ellen, Alsip, Chicago, Elk Grove, and McHenry. And the great thing about it is they keep a large stock of CoolBLUE at all locations. So you can just walk in and get your CoolBLUE and you're set to go.
Yes, thank you for the informative presentation. So DREISILKER is the authorized distributor for CoolBLUE in Illinois, Wisconsin, and Minnesota. And all of our counter representatives at our locations are able to help you out with any CoolBLUE questions you may have. You can reach out to us via phone, in person, at our counters, email, and also through our website, talking with our chat representatives. Thank you all for attending today. We will be sending an email tomorrow with a copy of this recording, and now we'll open it up to questions.
Anybody?
Earlier you mentioned that these work with DC motor drives. Do you put the choke around both the positive and negative, or do you use the NALAs or the separate ones, or how does that all work?
The installation is basically in the same in the AC system. You would put both the armature and the field lines through the CoolBLUE cores.
Armature and the fields.
Yeah, exactly.
Many of the DCs I work on have numerous very large conductors for the armature circuit. I don't think you make one big enough that could go around all of them.
Yeah, we'd have to look at our chart. I mean, we have some very large CoolBLUE cores that are used for the wind turbines.
Okay.
Yeah. So.
Hello, can anyone hear me?
Yes, Christy.
Oh, okay.
You want to comment on this?
If he could repeat the question, I'm sorry. I lost power, so I had to sign on with my phone.
I was asking about using them on DC motors.
Okay, the best way, I believe he said, was to run the armatures and the fields through the cores. But
Yeah.
there's a lot of cases where that's not possible. So then you would have to take the solution and apply one set to the fields and one set to the armatures.
Okay, that makes sense.
Okay, any other questions?
Just a real quick comment on the size of the cores too. We've got some cores up to 1 meter diameter, so we don't want to have to go that route if we don't have to, but we could wrap a building if we wanted to.
Okay.
Okay, well, if there aren't any other questions, thank you all for attending. And again, I will send out a recording to you tomorrow. Well, thank you all for attending, and have a great day.
Thank you.
Thank you, Lynn.
Thanks, Lynn.
Thank you.